Can you solve this problem using binary search? Let's try. So the question says a peak element is an element that is strictly greater than its neighbors. Okay. Given a zero indexed integer array nums, find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. So the array could contain multiple peaks and it's okay to return any of the peaks. Okay. And it also says that imagine that nums of -1 and nums of n, there is a like the number to the left of the first element and the number to the right of the last element of the array is minus infinity, which means like it's really a small number and the first element would always be greater than that number. Okay, so considered to be strictly greater than a neighbor that is outside the array. Okay, and it says that you must write an algorithm that runs in big O of log n time. Okay, then it shows two examples. So thing to notice here is that the array is not sorted. That is one thing, but we have to do it in big O of log n time. So this is our cue to use some kind of algorithm which is similar to binary search. Okay. If you look at the constraints, it also says that nums I is not equal to nums I plus 1. Okay, so no two consecutive numbers are going to be same, and this is going to be important for our solution, which we will see. Okay, so you should always read through the constraints and the problems. So let's try to understand the logic. So let's run the first example here. So it says 1 1 2 3 1, and we have to find the peak element. Okay, see, let me put the index. Okay, so I would calculate. So since we have to do it in big O of log n time, so what we would do it, let's try something. Let's try if binary search can work. Okay, although it's not sorted, but we should see. Okay, so let's calculate the middle index. So 0 plus 3 by 2, which is going to be 1, and we reach here. Okay, we'll see if this is a peak element or not. Okay, which is not, because 3 is greater than 2. Okay, so it's not. Now what should do? Like, we have to take a decision here as which part of the array we can discard. We are divided into two parts, like this is one part and this is another part, and we have to decide which part of this array we can discard and which part must contain a peak. Okay, so to understand the logic now, let's consider a hypothesis. So try to think of when can we have a peak, like what would be the pattern in the array when we have a peak. So for the peak to exist, we should have a pattern like this, right, where this element is greater than its neighbors. If this is mth element, then this would be m minus 1 and this would be m plus 1, and if this is greater than both of them, then this is my peak. So this is very important for the array, and if we have to avoid being no peak, then we have all the elements all the array elements should be along the same line, which means they all should have a same value, or they should be strictly increasing, or they should be strictly decreasing. Okay, to avoid this pattern. So this is important. Let's take 4 cases, okay, to solve this problem. So case number 1 is my happy case, where I found the peak, right? So there's nothing, like we found the peak, we compared it with neighbors, and the number came out to be greater than both of them. So that is our peak. We would just return that peak. Okay, now consider the second scenario. Okay, where, so I'm denoting m as the middle number, or the current number that we are checking. Okay, so this could be one of the case where the number m is smaller than m plus 1 1th number, but it is larger than m minus 1 number. Okay, another case could be this number m is larger than m plus 1th number, but it's smaller than m minus 1th number. Okay, this could be another case. Last case could be that this number is smaller than both m minus 1 and m plus 1. Okay, so let's see now. Let's take this case and try to put a hypothesis. Okay, so the hypothesis is that there will always be a peak on the side of the number which is greater. So in this case, in the first case, there will always be a peak on this side of the array. Okay, why? Let's try to see why. Let's try to contradict ourselves. Okay, so what I would do is I would say, okay, this is my last number. Okay, let's consider like e is my last number and there is no peak. How is that possible? Let's say all the numbers are same. Okay, okay, if all the numbers are same, then there is no peak, right? But this cannot happen. This is not possible because of our constraint, which says that no two consecutive numbers could be same. Okay, and also consider this, that whenever there is a peak, like we would see a structure like this, right? We would see a structure like this, right? At least, so there would at least be a structure like this where a number is greater than its neighbors, right? So if this is the case, there is no peak. Okay, how can we avoid like uh, how can we avoid like this so that there is no peak? If the end element is, and it goes like this, if the numbers in the array goes like this, right? Like strictly increasing order. But when this is the case, imagine, consider that the last element is minus infinity, and so in that case this is our peak. Okay, so it's guaranteed that even if this is the case, even if the numbers follow this pattern, like there's always a peak. Okay, what could happen if numbers follow this pattern? Okay, then you can see already that we found the pattern, peak pattern kind of, which is similar to this one. Okay, and in this case, like this is our peak, right? So our hypothesis holds, right? We said that whenever we follow the part of the array where on the side which is greater than m, we would always get the peak, and that hold here. Okay, we were not able to kind of discard the hypothesis. So let's consider another scenario. This case, the third case. Again, things are similar, right? What could happen is like, let me remove this. What could happen in this case is that again b could be here if all the numbers are same, which is not possible. B could be here to avoid the peak in between. But if this is the case, then again this number is minus infinity and this is our peak. Okay, or b could be here. Okay, which means that all the numbers between the first, b is my first number. Okay, so all the numbers between b and m minus 1 are going to be same. So if b is here, that means that all the numbers between b and m minus 1 are in strictly increasing order. But if this is the case, then this is my peak element. So again, my hypothesis hold, right? And the last one is nothing but you could follow like any path, right? Because it's just an accumulation of the previous two cases. So our hypothesis hold, and according to our hypothesis, there will always be a peak on the side of the element which is greater than the current number that we are checking, right? So let's take a look at the code of it. So this is the code that I have written for the logic. So first thing, so there's something to notice about this code, okay, which I'll explain. So the first things, let's take a look at the loop. Let's start with the loop. Okay, so this is my loop and I'll just calculate the m here. Okay, and then I would just check if nums m is greater than nums m minus 1. Okay, and nums m is greater than num m plus 1, which means that m is the peak, and that is our we would simply return m. Okay, if nums m is less than nums m minus 1, so nums m minus 1 is greater, and according to our hypothesis, we should check the left side of the remaining subarray. So we would set e to m minus 1. Okay, otherwise b would be set to m plus 1, and we would look at the right side of the current subarray. Okay, so these statements are very simple, very clear. Take a look at the loop condition, b plus 1 less e. Okay, why I have to put a condition like that? So if you take a look at the problem description, it says that there could be an array. So array length could be greater than equal to 1, which means there could be 1 element, 2 element, 3 elements. Okay, but consider but this logic to like this is to make sure this b plus 1 equals e condition is to make sure that we don't fall off. I mean, if we are looking into this array, then we don't have to take care of the edge cases separately. Okay, why? Because this condition makes sure that there is at least like the loop will only run when there are at least like 3 elements. Okay, so you see in this b plus 1 less e, so in this case, like if this is my loop, like let's say this is b, this is e, so b plus 1 is less e, this holds here. But if you take any loop, like any array which is less than size 3, then this condition would not hold. Okay, and our loop would break, and in that case we would have to put checks separately to find the peak. Okay, so that is what I have done in this line and in this line. Okay, or in these two lines. What I have done is this is this is for the case where we have the array of length 1, and this is for the case where the array is of length 2. Okay, sub array of length 2. So that's how we implemented this. You can write the code for it, and that should succeed. In the next video, we will see some examples of min-max patterns and how to solve them with binary search. Thanks for watching this video.